All right, guys, you are welcome to class. My name is Green, and this is Green Notes Physics. So today we are going to be looking at something very, very important in physics, and it is going to be for you if you are studying physics or you are doing engineering and you are taking a course that has to do with modern physics, solid state physics, or even quantum physics. So that means that if you are in your second year or third year, this content here is meant for you. So don't miss this content at all. Make sure you stay glued to the very end. We are going to be talking about something very, very important in physics. Now, for the past 2 to 3 weeks, or even over a month now, I've been posting content here as regards JAM physics. So I am not just a JAM tutor. We are just running a program right now at Tuteria where we are preparing students for the upcoming UTME exam. It's a rigorous program. It's a 4-month program. It started last month, and we are preparing students for the UTME exam, whether the student is in art or commercial or even sciences. We are having live classes from Mondays to Fridays. Yeah, Tuteria. It's a virtual class actually, so you can join from anywhere. So if you have your siblings, you have your family members that needs to join a rigorous training program for the upcoming UTME, Tuteria is the best place to be. The program is just 35,000 naira for the entire 4 months. Yes, just 35,000 naira. That's less than 9,000 naira a month, and you cannot get that from anywhere. Trust me. With the fact that we have incredible tutors that are going to be teaching your siblings or even you. We have incredible tutors on ground. We have the students. We have access to a web app where they are going to be getting weekly practice questions. They are going to be getting daily questions. They are going to be getting monthly mock exams. Yes, monthly mock exam, apart from their weekly live classes, daily live classes from Monday to Friday. So basically, it's a total package. It's a complete package that when a student attend this program from the very beginning to the very end, that student will surely get over 300 in the main UTME exam. So if you are there, or you have a sibling, or you have a friend that is preparing for UTME, tell the person to subscribe to Tutorial Prep program for 5,000 naira only. Now, the another thing is that when they join, they will have access to everything that has been done, because classes are actually recorded. So on their dashboard, when we onboard them, they will have access to everything that we have done, and there is a plan to actually track their progress from the very beginning to the very end of the program. So join us. Now, like I said, today we are doing something different. What is that? Step potential. Step potential. Step potential. Step potential is that important concept that I want to talk about today. And like I said, it's going to be useful for students in their second or third year in physics or engineering, for solid state physics courses, or modern physics course, or even quantum mechanics course, the very beginning part of quantum mechanics. It is very important. It is very important to listen if you are in this particular category. Now, step potential. What are we talking about? Now, step potential is a very important and very popular model in quantum mechanics that helps us to clearly understand the distinction between the classical world and the quantum world. Of course, quantum mechanics is that aspect of physics that has to do with the study of things in a microscopic level, things that are very, very small that the human eye cannot even see. So that is what quantum mechanics is all about. Now, step potential is that model that tells us more about the fact that, classical mechanics is not enough to explain some things that happen in the universe. Quantum mechanics is that fundamental, that foundational, it gives the foundational explanation to everything that occurs in the universe. So what is the idea of step potential? This is what we are saying. So we have what we call a step function. So if I have a step function, if I have a potential, this is a potential which is a function of x. That potential has a value of 0 when x is less than 0, and has a value of v naught, which is some constant, immediately x is greater than or equal to 0. So what are we saying? We are saying that typically if I have a particle that is moving, so I have a particle that is, so let's assume that this place here is when x is equal to 0. So this is our x-axis here, x equal to 0 at this point, and x tends to positive infinity here, x tends to negative infinity here. So if I have a particle that is coming from this side here, where the potential is 0, when x is less than 0, this side here, the potential is 0. The particle is basically a free particle at this side here, because there is no potential at this side here. Now, then we are now saying that the particle suddenly encounters a barrier. So the potential is 0 at this point here. Then immediately x equal to 0, the potential, which was 0 before, went up drastically. From 0, it went up drastically to a value. So the potential that was 0 before, so v of x is equal to 0 when x is less than 0. Then immediately x equal to 0, v of x became v naught. So I have a particle of mass m with an energy E. The particle is there, it is moving from this side where the potential is 0, so it is moving freely. Then immediately it encounters this barrier, this potential barrier, where the potential became v naught at x equal to 0 and remained v naught as x is greater than 0. So our concept here, our idea is to study the motion. We want to understand what will happen to this particle here. It has an energy E. When it is coming like this, it encounters the barrier. What will happen to it? Will it be transmitted? Will it be reflected? What will happen to this particular particle here? So we are going to be discussing this concept in two cases. The first case will be when the energy of that particle is greater than the potential v naught encountered there. What will happen? So according to classical mechanics, since the energy of this particle is more than the potential here, as the particle is coming, the energy is more than the potential it encounters here. Classically, we expect that immediately it encounters this barrier, because the energy is more than the potential energy of this barrier, the particle is expected to still be transmitted. The entire particle will be transmitted, and there will be no form of reflection. The particle will not be reflected at all, because the energy is greater than what? Is greater than v naught. That is what classical mechanics. In fact, if I throw this ball like this, let's assume there's a barrier like this. If I throw this ball like this, if the energy of this the energy of throw, the energy with which I throw this ball is more than this barrier here, this guy will knock off this guy and continue to move. Basically, that's how the classical world paints this situation. But in quantum mechanics, we understand that this particle here is not just a particle, it is equally a wave. This is a matter wave. It is a matter wave. This is a matter wave. So that means that when this particle encounters this barrier, when it encounters this potential, even though the energy is greater than the potential here, we are saying that because quantum mechanics is probabilistic, it is not deterministic like the classical mechanics, we are saying that when this particle, because it's a wave, it behaves like a wave. When, of course, wave-particle duality, so this particle also has some wave attributes. Now, when it encounters this barrier, according to quantum mechanics, that particle, there is a probability, there is a chance that some portion of the particle will be transmitted, while there will be some portion of the particle that will be what? Reflected, quantum mechanically. That this particle that is moving on encountering this barrier here, this potential here at x equal to 0, some portion of it will what? Will be transmitted, while some portion of it will be what? Reflected, because this is a wave. It will behave just like your normal light wave. So if a light wave strikes a barrier, there can be reflection. There can be what? Reflection, there can be refraction. So we are saying that this particle here, even though the energy is greater than v naught, and classically we are saying that the entire guy should be transmitted. But according to quantum mechanics, there is a chance. There is a chance that this particle will be reflected and some portion of it will be what? Transmitted. even when E is greater than V naught. So our focus in step potential is to discuss that quantum theory and try to find the probability of the reflection and the probability of the what? Transmission. Meaning we are interested in determining what we call the transmission coefficient and also the what? Reflection coefficient. And if what we have done is very, very accurate, we will realize that the sum of the transmission and reflection coefficient must be equal to 1. The sum of the two must be equal to 1. So our focus is to find T, which is the transmission coefficient, and R, which is the reflection coefficient. And that T plus R must give us 1. That is what we want to do. Now, whenever you are analyzing a quantum system, the starting point is solving a Schrödinger equation. Solve the time-independent Schrödinger equation, and that is where we are going to start the process from. We will solve the time-independent Schrödinger equation. So let's go and start the process. So again, we are discussing step potential. And what's happening? This is a situation of things, and this is case 1. When the energy of the particle is more than the potential V naught. So the potential here V of x here is equal to 0. But immediately, that's when x is less than 0. This is this region here. Let me call it region 1. Region 1, when x is less than 0. This point here is when x equal to 0. And this other part here, this second part here, is when x is greater than 0. So we have a step function. So you might not have the question given as this. They can just give you a step function. What's the step function? That v of x is 0 when x is less than 0, and v naught when x is greater than or equal to 0. So once you see a step function like this, you should know that, oh, they're talking about the case of a step potential. This is what we tell you that we are dealing with a step potential, because this is what we call a step function. When a function is 0, when x is less than 0, and the function is now a value, it went up drastically to some value at x equal to 0 and when x is greater than 0. So it maintained v of x became v naught. Immediately x became 0 and maintained that value as x tends towards positive infinity. Yeah, x tends towards negative infinity here. All right. So the starting point, like I said, is solving the time-independent Schrödinger equation. So from the time-independent Schrödinger equation, what's that equation? Minus h cos square over 2m del square psi of x over del x square plus v of x psi of x equals to e psi of x. This is our TISC, our time-independent Schrödinger equation. All right, so we have this equation. We are going to solve the equation for the two regions. So this is region 1 when x is less than 0, and this is the second region. This is region 2. Region 2 when x is greater than or equal to 0. So we are going to start for x less than 0 region. For that region, for x less than 0, that's region 1. What's happening? At that point in time, v of x is equal to what? 0 in this region here. The particle is coming from here like this. This is a particle. It is coming like this. It has an energy that is greater than what? The potential here. So we are dealing with this region first. So for this first region here, what is happening at this first region? V of x is equal to 0. So if I put v of x equal to 0 here, this guy will cancel out. So what am I going to have now? I have minus h cot square over 2m. Then I have, now, this thing here is the partial derivative del. This is partial del squares of x del x square. So we are differentiating psi. This psi, which is our wave function or the eigenfunction. Let's call it the eigenfunction here because the full wave function is a function of x and t. We are dealing with one-dimensional situation. So just x. We are saying the particle is only moving along one dimension. So this is the full wave function. The full wave function is psi, and it is equal to what? The small letter psi of x times the energy term minus iota, what is it called? E over h cot t. This is the full wave function. But our focus is just the eigenfunction here. But that's just by the way. That's by the way. Let's come back to class. So if you look at this, we are saying, okay, differentiate psi, which is a function of x, partially with respect to x twice. Now, we use this del here if we are dealing with more than one independent variable. But in this case, x is the only independent variable that we have. So that means that instead of using del, I can just use our normal d, which is for the normal total derivative. So instead of using del here, I will use what? D, because we are dealing with what? Only one variable. So we are not, we don't need to be differentiating partially. Just differentiate directly, meaning do a total derivative. So instead of using del, because it is just x, and even it is a 2D situation where psi is a function of x and y, then it should remain del. But because psi is just a function of x, then I can, instead of writing del, I can write my d. All right, okay. So, so in this region, this guy is 0. What will I have here? So I'm going to, instead of writing del again, I will change it to d square psi of x over dx square. Over dx square. Then this part is already 0. So what do we have? Equal to e psi of x. Now, because I'm dealing with region 1, I will do my labeling properly. I will call this my psi 1. I will call this psi 1 to just indicate that I'm dealing with the first region, psi 1. All right, so if I separate properly, multiply all through by 2m over h cot square, I will have minus d square psi 1 of x dx square equal to multiply by 2m, that's 2m e over h cot square. Then we have what? Psi 1 of x. This negative, I multiply negative by both sides, it will leave here and it will come here. All right, so from here, I can bring this guy over here. So I have what? D square psi 1 of x over dx square plus 2me upon h cot square psi 1 of x equal to what? 0. All right. Now, from de Broglie and Planck-Einstein equation, 2me over h cot square is actually k square, the wave number square. So let k square, I don't have to be showing that derivation, but you should know that k square is actually this guy. The square of the wave number will give you 2me over h cot square. So if I do that substitution, now again, because I am dealing with region 1, I will call this one k1 as well. So if I substitute back there, I have d square psi 1 of x dx square plus k1 square psi 1 of x equal to 0. This is a second order ODE, which I can solve. So this is a second order ODE. Solving the second order ODE. So if I assume that the solution is is exponential mx from your basic 100 level ordinary differential equation, you should be able to solve this second order ODE. So you will realize that this is more or less like saying, let me just do something here. This is like saying, remember you represent the derivative with m. That's our very small shortcut. M squared, this will be m squared plus k1 squared equals 0. So I have m squared equals to minus k1 squared. That means m will be plus or minus iota k1. This is what I'm going to have. So remember, we used to write our solution. The solution will be C1, that's constant, exponential, M1. This plus or minus means that I can break down the solution to M1 equal to the positive one first. That's iota K1. And the second one will be what? Negative iota K1. This is iota. Iota as in square root of what? Minus 1. This iota is square root of -1 from your complex number, the imaginary unit. So you write your solution as C1 exponential m1x plus C2 exponential m2x. Remember your ordinary differential equation. So my m1 is this guy, my m2 is this guy. So if I use this concept here, so if you solve this second order ODE, you must know how to solve these basic guys. If you solve this second order ODE, the solution for our psi1 of x will be a exponential. So I'm using a as my constant here. So a exponential iota k1x plus b exponential minus iota k1x. That's the solution. I can call this my equation 1. So this is the solution for the eigenfunction on this region here, on this side here. So I will go again to the second region. So for x greater than or equal to 0, the second region, that's region 2. What's happening at region 2? At region 2, v of x is what? From the step function given, v of x is what? Is v0. It is v0, it is not 0. So if I come back to my TISC, my Schrodinger equation, v of x is now what now? v0. Of course, I'm changing this del to normal d. So what do I have from there? What do I have from there? So I have minus h cot square over 2m d square, right? The second derivative of psi. Remember, I'm dealing with region 2 now, so I can call this one psi 2. So dx square plus vx is now, v of x is now what now? v0 psi 2 of x equal to e psi 2 of x. If I transfer this over here, I have negative of h cos square over 2m d square psi 2 of x dx square equal to e psi 2 of x minus v0 psi 2 of x. So we have this. So from here, you can see clearly here that we have e minus v0 and psi 2 is common. Psi 2 of x is common. And I have minus h cos square over 2m d square psi 2 of x over dx square. So the same thing here, I can multiply both sides by 2m over h cos square. So if I do that, a negative 2m over h cos square, if I do that, I will be left with d square psi 2 of x dx square equal to negative 2m into what now? E minus v0 over h cos square. Then I have what? Psi 2 of x. I can bring this guy over here. So I have the second derivative of this guy with respect to x plus 2m e minus v0 over h cos square psi what? Psi 2 of x equal to 0. Bring it over here. So the same thing here, if you look at this, this is just energy minus a number. V0 is just a number, a constant. So this thing here, I can call it K2 square. Just like I call this one K1 square. So let K2 square, let it be what this time around? 2me minus V0 over, they are dimensionally correct actually. So over h cos square. So if I do that, I'll have d square psi 2 of x dx square plus k2 square psi 2 of x equal to 0. This is also our second order ODE. So solve the ODE. Solve the ODE. If I solve this second order ODE, this one will also give me, just like that guy, this one will give me what? Psi 2 of x equal to, I've used a there and b, so let me start from c. C exponential iota k2x plus d exponential minus iota k2x, equation 2. This is the solution. So the wave function here has a solution psi 1. The particle has a solution for its, when we solve this Schrodinger equation for this region, we got psi 1. Then in this region, we got what? Psi 2. All right. So from our solution, what can we deduce? What does it mean? What is the meaning of this solution here? If you look at this, this is a wave equation. This is a wave solution. This is a wave solution here. It's a wave solution here. And it's a wave solution. A here is just the amplitude of this particular part here. B is also the amplitude of this particular guy here. C is also the amplitude. D is also what? The amplitude. But what exactly does it mean? So if I go to my Psi 1, I want to do some breakdown here in my Psi 1. So I will not wipe the diagram. Let me wipe this. So if I go to my Psi 1 is Psi 1 of x is actually a exponential iota k1x plus b exponential negative iota k1x. Now, the meaning of this solution is this. The particle has some complex numbers. Remember, a wave function is just a complex number. It's just a complex function. It does not make any meaning. It does not have any meaning on its own. But it contains some things that we can extract in order to explain what is happening to the system. Now, the meaning we can infer from this solution is the fact that this portion here, look at it, this one is positive, which is telling me that the body or the particle or the wave that has this particular portion of the equation is going to the right. It's going towards positive x direction. Why negative x here means that that portion of the wave is going towards what? Negative x direction. So that means that as the particle is moving, are you there? There is some portion of that particle. We have some portion of the particle that will continue, that is going in this direction, which is this guy. And we are going to have some portion on encountering this barrier. We are going to have some portion of the particle that will what? That will be reflected. That will go back in the negative x direction. Go back like this. That means that this guy here is actually the incident wave. This is the incident wave. It is the one going like this. So I can say from here, my psi incident of x is actually a exponential iota k1x. That is the incident guy. And my psi reflected will be this other guy, b exponential iota k1x. So this particle that is moving, a portion of the particle, because the particle is also behaving like a matter wave, there's a portion of the particle that is going to go forward, the incident guy, while some amount of it will be reflected back. Even though E is greater than V naught, there will be some form of reflection. So the wave equation explaining that is this portion for the incident, for the one going forward, while for the reflection will be this. Take note of this. So let me call this. So let me just leave it like that. Then if I go to the second psi, psi 2 of x equal to c exponential iota k2x plus d exponential minus iota k2x. Now, there's something called a well-behaved wave function. Not all wave functions are usable. Not all wave functions are used to explain what is happening in your quantum system. The wave function must satisfy some conditions. You must look at the wave function and see whether the entire portion of the wave function is making sense. Does it make sense in accordance to what the system is saying? Our psi 2 is this. And from what we have explained, psi 2 is the wave in this region. Oh, the particle has entered into this region here. Now, the positive one is saying that it is going forward. It has entered there, meaning it has transmitted like this. So it's still going forward. So there's transmission. So that means that in essence, we can say this guy here is the transmitted wave because it's the one going forward in this region 2. It encountered the barrier because the energy is more. Then it went into this second region and continued. So this is the positive X guy. That's the transmitted wave. That's the transmitted wave. However, am I now saying that this guy, it means that there's a wave that is going back? Yes, that's the meaning of this. But does it make sense? The particle encountered the barrier at this point, the potential at this point. Some amount of it was reflected back, while some amount of it was what? Transmitted. Now, this transmission is, this potential here is still infinity. So the transmission started. The transmission has started like this, and the potential is constant. As x tends towards infinity, the potential is constant. but there is transmission here. Now, are we now saying that even when the potential is not changing, the potential will not change at all? Are we now saying that there will be a time where that particle will now be reflected in this region here? The particle will not reflect again in this region here unless it encountered another barrier. Unless there's another barrier that has a potential that is different from that there's a change in potential now, and that potential now what? Because of that change in potential, then there might now be what? Reflection. But in this case, the potential is constant as x tends to infinity. So as that particle is being transmitted in this region here, there will be no form of reflection back. It will not be reflected because there's no other barrier here. There is no change in the potential at all in this region. So that means that this portion of this solution does not make sense. That means that I can say, let D be equal to 0. The amplitude of the wave that we are saying will go back, let it be 0. The amplitude is 0 because there's nothing that will go back in this region here. So if D is 0, that means that this portion will go out. That means that our actual side 2 of x should be C exponential iota k2x. That is equation 3. That is our actual side 2. Because there will be no form of what? Reflection in this region. As the what? Potential remain constant as x tends towards infinity. So if this is the case, that means this is just our transmitted wave. So I have my side transmitted of x is just the C exponential iota k2x. So I have this guy here. Now, the next thing is, remember our focus, the major thing we want to get is the reflection coefficient and the transmission coefficient. And to get that, we need to know what these amplitudes are. We have 3 amplitudes now. The amplitude here, which is C, where is that guy? The amplitude A here, which is the amplitude of the incident wave. The amplitude B, which is the amplitude of the what? Reflected wave. And C, the amplitude of the transmitted wave. It is these amplitudes that will tell us, that will give us a picture of how the probability of transmission will look like and probability of what? Reflection. So what's the next thing to do? We need to apply what we call the boundary conditions. We apply our boundary conditions because remember, there is what we call a well-behaved wave function. Before you can say this psi is a wave function, it must satisfy some conditions. One of the conditions is the fact that what? It must be continuous. And not just psi being continuous, even its derivatives must be continuous. It must be continuous. It must be normalized. Yes, it must be normalized. So we have so many conditions that must be satisfied for a wave function to be well behaved. So what are we going to do now? We are going to apply one of these conditions, which is what we call the boundary condition. But then we are applying the continuity condition here for the boundary. The only boundary that we have. So apply boundary condition. For continuity. The wave should be continuous at a particular boundary. So what are we saying? As this wave is coming like this, when it gets to x equal to 0, it should continue like this. There should not be a jump, meaning as it's coming like this, when it gets here, it should not, at x equal to 0, it should not now continue like this. We must not have something like this. This is what we call discontinuity. The wave function cannot be like this. This is a region here. This is region 1. So we have psi 1 in this region 1. We have psi 2 in this region 2. The fact that they are different does not mean that when it gets to this region, it should not break. They should not break. No, we must not have this. This is discontinuity. We must have a situation where, as this guy is coming like this from region 1, when it gets to the boundary here, it should continue. It should continue from this point. It should continue from this point. That's continuity. It should continue from this point. It should continue from this point. Psi 2. So what are we basically saying? The first condition we are applying is the fact that psi 1 at x equal to 0 at that boundary, when it gets to that boundary, must still be equal to psi 2 at x equal to 0. It should continue from there into the second region. It should continue from there into the second region. All right. So basically, from here now, we'll just go back to our psi 1 and psi 2. Remember, what's psi 1 of x again? Psi 1 is a exponential iota k1x plus b exponential minus iota k1x. And psi 2 of x is c exponential iota k2x. So we're going to apply our boundary conditions for this and see what we are going to have. So for the first one, when x is 0 here, if I put x as 0 here, psi 1 of when x equal to 0. When x is 0 here, e raised to power 0, everything will be 0. E raised to power 0 is 1. 1 times a is a, plus e raised to power 0 is also 1. E raised to power 0 is 1 here. 1 times b is b, so I have this. Why for this, psi 2, when x equal to 0, this is 0, so 1 times c is what? C. So we are saying that they must be equal to each other. Therefore, we are saying a plus b must equal to c, equation 4. That's the first, using the first boundary, the first condition. The second condition is that it is not only the wave function itself that must be continuous. The derivative must also be continuous. Meaning that if I differentiate psi 1 at x equal to 0 with respect to x, it must give me derivative of psi 2 at x equal to 0 with respect to x.